Okay, so today let's fix on uh, the deflection and stiffness of the components or the mechanical parts. Okay, so so what's the elasticity is? So I think you guys already learned the materials mechanics. So in the materials mechanics course, define the elasticity, which is the property of the materials that enables it to regain its original configuration after deformation, right? That's mean any being like any components or a being is subjecting to a stress. And after the stress released, the dimension will return, okay, right? Return to its original one. Okay. So we can model this as a spring. So spring is a mechanical element that exerts a force when deformed, right? So, so if we look into a being which with two reactions, okay, so the two boundary condition of these two ends of this being, right? So we can simply imagine that the deformation y is linearly proportional to the force applied to it, right? Okay, so this relation between the force versus deflection is linear. Okay, so the second case is that the reaction force at two end, which is restricted, uh, deform in y direction. Okay, so when a force applied to it, the relation between force and deflection, I mean the deflection is proportional to the force applied to it, right? However, the relation is nonlinear. Okay, it's nonlinear. Okay, and the third case is that suppose we have the soft membrane. Okay, so you can think of uh, uh, a balloon, right? A balloon when you stretch it, or you can just deform as a membrane, disc membrane, right? So when we apply a force, right, any force to this softening spring, or okay, so this figure maybe draw in the opposite direction. So what I mentioned, the balloon, the disc membrane is one type of the softening spring. Okay, and in this case, it's just like for example, it's say it's the rubber band with a little bit high stiffness. It's a rubber band, okay? It's in a disc shape, okay? So when we apply a force, it will deform, right? It will deform. And this deformation basically is nonlinear to the applied force. Okay, and it is proportional to the applied force with a specific elongation or with a specific force applied. When the force is beyond the limit, right, and the force will decrease. Okay, so when the force applied to this softening spring, it can be a rubber disc membrane, okay, or any kind of things like that. Okay, so initially the force is proportional to the deflection, right? When the force reach the limit, right, and the deflection is still going, right? It's still elongating. However, the force decays. Okay, the force decrease when this elongation increase. Okay. Okay, so So we can define the relation between the force and the deflection. The force is a function of the deflection, right? So for the spring rate, the definition of the spring rate as the take the limitation, right, of the delta F over delta Y. When the delta Y approach to zero, we can rewrite it in the derivative term, right? A derivative formation. So for the linear spring, so remember it's a linear spring, K is a constant called spring constant. So K equals to F divided by Y, the deflection. Okay. So when the any components or being, as what we already taught in the previous courses, that for the membrane is subjecting to the actually load, it's deformation. The deformation delta equals to F, the applied force, times the dimension, the length of the beam or components divided by the cross section and the Young's modulus. Right? So for the spring constant for this component or this beam is elastic. So we can define the spring constant K equals to F over delta, right? F over delta. So just plug this delta in the denominator here. So the spring constant equals to AE over L, A of L. So the spring constant is for the linear behavior of the axial loading, For the torsion, we have to regard this deflection from the delta to the angular deflection. Okay, so the angular deflection of the uniform solid or the hollow round bar subjected to a twisting moment T. So we say the twist angle. So previous slide, I just used the phi to define the twist angle. It's the same thing, okay? It's the same definition. So equals to the torque times the length of the solid rod divided by the shear rigidity and the polar moment, right? The polar moment. And also can convert this twist angle from the radius to degree, okay? The degree. Okay, so the similar approach, so we can figure out the spring, the torsional spring constant for a round bar, K equals to the torque divided by the twist angle equals to the GJ divided by I, GJ divided by I, okay? Okay, so let's recap the curvature of the beam subjected to the pure bending moment, right? So the curvature, low, right? 1 over low equals to the moment divided by the EI. Sorry, this is not L, it should be I here. It's just a typo, okay? It's a typo, it should be I here. Okay, so from mathematical deformation, the curvature of the plane's curve, right? This is the deformation, right? So the slope of the beam at any point x along the length theta equals to dy dx. Okay, so if the slope is very small, that means this component or this beam is totally elastic. The denominator here approach to unity, right? Because this will approach to zero. Okay, approach to zero because this term is approach to zero. Okay, so we can plot this curvature right here. So we can figure out the relation between the moment and the deflection, right? So here's a wrong typo, it should be I. Okay. Okay, so just recap what we already learned for the pure bending, right? The shear equals to the derivative of the moment with respect to x, okay? And the stress distribution equals to the second derivative of the moment with respect to x, and the derivative of the shear with respect to x, right? So it can be successfully differentiating, okay? Successfully differentiating, right? Right? So as what I mentioned, the relation between the moment and the deflection, or the double derivative of the deflection, equals to m over ei, right? So we can take the derivative, right? Take the derivative, we get the shear force, right? Shear force, and to take the derivative again, we get a stress for the loading, the loading, okay? Okay, so and then we just plot this shear and bending moment diagram, right? From the loading or the stress from the previous one. Okay, from the previous one. Okay, so this Q, including the distributed load and the central load, right? Including the distributed load and central load. Okay, so and then we just integrate, take the integration of this Q, right? This Q, we got the shear. Okay, and then we take the integration of the shear, we get the moment. Okay, and then we take the integration, we get the theta, which is the slope, right? And then we take the integration, we get the deflection. This is what we want, right? Okay, so if we can figure out the loading, okay, we can just draw this free body diagram and we take the integration, so we can figure out its shear force diagram, right? So in this case, the distributed load is constant, right? It's a flat. So after integration, the flat will turn into a linear line with a slope, right? And then we take the integration of this linear line, we'll get the say the parabolic, the second order, and we take the integration of this is a moment diagram, right? It's a bending moment diagram, and we take the integration of this bending moment diagram, we get the theta, right? The slope, okay? And then we take the integration, we'll figure out what is the deflection is, right? So we can figure out the deflection at different point, different x location, right? So you should find out where's the maximum deflection, right? Okay, so how to evaluate the beam deflection? So previously we already introduced the singularity function, right? The singularity function, and also we already play around the NC softwares, right? So you must roughly realize how to use the software simulating the deflection or the force or the stress distribution, right? And then we can still use the superposition. We just add up those deflection with respect to the different loading, just add them up together, we can figure out what this deflection is. Okay, and the moment area method, we just plot this shear and bending moment diagram, right? And here I'm gonna introduce the methods called the Cartesian theory, Cartesian energy theory. Okay, and this final element is related to the numerical analysis. Okay, so I'm gonna skip this. I'm gonna skip this one. So I'm gonna focus on the Cartesian energy method. Okay, so superposition determines the effect of each load separately, then adds those results. And separate parts are solved use any method for simple load cases. And many load cases and boundary conditions are solved and available in the table 9 of our textbook. Okay. So for the condition to use the superposition or to use the those method I've already mentioned previously, each effect is linear. Remember, linear related to the load, linear related to the load. And load does not create a condition that affects the result of another load. Okay, so the condition of the force will only create one deflection, which will not affect the other results. Okay, and the deformation resulting from any specific load are not large enough to appreciably alter the geometric relation of the parts of the structure system. Okay. Okay, so that's mean this deflection or this deformation is not so large, or it's a small, very small. It's very small. Okay, it's very small. Okay, so this is one example. So one example here, so from this figure, which is a cantilever beam with an end load, right? So it's a cantilever beam with the end load. Well, you would just think, well, it's quite easy, right? It's not a, it's a common question, it's just a cantilever beam, okay? Right? However, in this case, because we only consider this case as the rigid from your those mechanics course that you learned, we always consider this cantilever beam as rigid. And the support, the boundary condition is also rigid. Okay? So you will think of, oh, well, it's not so difficult. Why we have to mention this questions again here? So why I have to mention these questions again here? So you can see the questions mentioned that after testing the rigidity of the wall, it was found that the translational stiffness of the wall was Kt, which is the force per unit vertical deflection. And the rotational stiffness was Kr, so moment per unit angular deflection. So what's this mean? This means this left support is not rigid. So what's that mean? That means you can think of that there's a solid rod or a cantilever being just embedded into a wall, right? And this wood, maybe it's a clay or it's some mud, right? So this wall, if we just insert a beam or rod here, okay? And if this wall is not rigid, for example, it's the mud, right? So when you apply a end load here, it will deflect it, right? It will deflect it. right? And also at this boundary condition, it will move, right? Because it is not rigid. The boundary condition, the left end support, it's not rigid. It's a mud. Okay, so when you apply a force, right, the end point will just move vertically, right? So when this end point, this boundary condition can move vertically, of course it will rotate it, right? It will rotate it, right? So if this boundary condition is rigid, so we will think this being maybe like this, right? The theta here equals to 0, and this delta x equals to delta y equals to 0 for the boundary condition, right? So that means at this point, if it is rigid support, this point will not move vertically or horizontally. Also, the slope is zero. However, in this case, suppose this left end support is not rigid like a mud, right? So the left end will move, right, vertically. Also, it will rotate it, have a slope, theta here. So we have to model this boundary condition, the left end boundary condition with the two stiffness, KT and KR, with the translational stiffness and the rotational stiffness. Okay. So first we have the translation, right? Due to the compression of the spring KT and the rotational stiffness or rotational spring constant, spring rate, right? So we can define the y1. One is the point right here, okay? The point here, point 1, right here. Okay. So for the y1, due to the KT, right? So that's mean the left end will move vertically equals to F over KT. Also, it will rotate it at this left end, right? Left support end, right? So the moment in the spring constant KT equals to is the moment in the spring constant KT is the M1 at the point 1 equals to F times L. L is the length of this rod, right? And this gives the counterclockwise rotation theta equals to FL over KR. Okay, so consider this mode of deflection only. The beam rotates rigidly clockwise, leading to the deflection, Y2. So there are two deflections. One is from the translational, and the second one is from the rotation. Translation and rotation. Okay. Okay, so the final one, we have to consider the elastic deformation, right? So from your materials mechanics course, you can check any table or handbooks, right, to figure out if this beam is rigid. It is rigid. If it is rigid, right? So we can figure out the deflection, right? The deflection right here is Y3. If what I say is if this beam is this left support is rigid, okay, so we can figure out this elastic deformation of the beam, okay, and we define it as Y3. So right now we have three parts, three deflections. One is the rotational, and the translational, and the elastic, right? So for the Y3, you can check any table for the cantilever beam, right? It's not quite difficult. So we have 3 deflection. 1, right? The elastic. The 2 KT is the translational. That's mean the left end will move vertically, and the KR, right? The KR, the rotational. Okay, you got it? Okay, so for right? So this is the final term we get it. The deflection including the three deformation. Okay, 3 deformation. Okay. Okay. So and this is what I already taught previously. This is the singularity function, right? So I just skip this. Okay, skip this. I think it's not so difficult. Okay, I skip this examples here. Okay, it's just singularity function, and you can just study by yourself. Okay, so I'm gonna jump into the string energy. What's this most? Yeah, this the key issues I'm gonna discuss. Okay, so for the external work down on elastic, remember elastic member in deforming, it is transformed into strain energy or the potential energy. Its strain energy equals to product of average force and deflection. So in this case, the force versus the deflection, which is a linear, right? It's just a linear, right? And the product of the average force and the deflection U is the area under the force and deflection figure, right? So this area. Okay, is the area. So we can write it in the term of the half of the F times Y, right? And we can just convert it into the spring constant, right? So the strain energy equal to the F squared divided by 2K, okay, divided by 2K. Okay, so there's a case study here. So what's the suppose we have 2 cars. One is say it's a Volvo, and the second one is Toyota. So if these 2 cars just collide each other, or they just hit the wall, so I say which one is stronger? Well, sorry, I cannot ask this kind of question. I should ask which one is safer for the driver and the passengers, and why. Okay, explain your answer, and you can discuss your answer from the strain energy point of view. Okay, and which will by, okay, anyway, it's not the real questions related to our course. I just want to, just trigger your interest. Okay, so which one is safer for the driver and passenger? So we can think of this way. So for the Volvo, we know it's a frame or the structure of the car is really strong, right? You have very thick, right? Thick structure, okay? Or strong structure for this whole vehicles. Okay, that's mean I'm stronger than you, right? I'm stronger than you, and you will be destroyed. And the drivers in mine will be safe. Okay, so on the other hand, usually we'll think the structure of the Toyota's car is not so strong, right? not so strong. However, I will say the structure of Toyota's car has a huge strain energy, or say have the huge toughness. What's that mean? That means when this Toyota's car collides to a wall or just have the car accident, those frame or the whole structure will observe the most of the deformation energy when it is collide or its impact or no. So when this structure, the car structure absorbs the most of the energy, that means the passenger will not be hurt, right? Because those structure already, maybe the car is almost squeeze or crash. However, the passenger and drivers are safe because those deformation energy already being absorbed by the car structure itself. Okay. So it is different from, the toughness or the strain energy is different from the strength, right? So you say, well, it's elastic. So if I make a rubber car, right? A rubber, you can think of the property of the rubber, right? So when you stretch it or you just press it, after the force released, this rubber will return its original shape, right? Also, it's elastic. You can think of this way: if a car is made of, rubber, so when it's clad, what's gonna go happen? So it's clad or it's hit or it's have a car accident, right? After force released, the rubber will return to its original car shape. However, the driver inside this rubber car will become a pancake, right? Will become a pancake. Okay? Okay, so this is one example of strain energy and the additional energy associated with the incremental load, dF. Okay, so we apply a small load, incremental load, which is corresponding to the additional energy. You will say that the additional energy equals to y deflection times the incremental load. And we can solve the deflection equals to du df. That means we take the derivative of the u, the energy, the strain energy, with respect to force. Okay, so this is the incremental force, okay, to causes the additional energy. Okay, so we say when forces act on elastic system subjected to small displacement. Remember, small displacement, and this displacement delta I corresponding to any force I, Fi, in the direction of the force is equal to the partial derivative of the total strain energy with respect to that force. So what is the Cartesian theory? This is the Cartesian theory. Okay, also for the rotation displacement, this is the Cartesian theory. Okay. Okay. So what's the definition of the Cartesian theory? So for the definition, the work equals to the force dot the displacement, right? So the energy, the additional energy equals to dF, right? The incremental force times the delta, the deflection. Therefore, the deflection or deformation equals to the energy partial derivative with respect to that force, right? Okay, this is called the Cartesian theory. Okay, therefore we can define the delta I equals to the energy take the derivative with respect to Fi. Okay, so suppose we have the cantilever beam again, right? So there's a point load applied to the free end. As remember, previously we mentioned the deflection is small, or the displacement is small. So the theta is small, right? The theta is small, right? Therefore, can define the deflection equals to r theta. R is the length of this beam, right? Theta is the slope or this angle. Okay, and the moment equals to F times R. Okay, and the du, the additional energy equals to the incremental force times the deflection, right? And we can replace this delta with r theta. R theta, right? And we can replace the df, what? The df, the f, right? Okay, so we can replace the df and the delta, right? Convert it into the relation of the m and the theta, right? And we just rearrange this equation. We get the theta equals to the partial derivative of the energy with respect to the moment, right? The moment. So we get this relation. Okay. So from the definition at the very beginning, the straight energy U equals to F over 2 times the delta, right? The average between the F1 and F2, 0 to F. Okay, so I'm just summarize the energy with respect to different condition. So first is the actual loading, right? So this is the delta, the deformation, and this is the straight energy, right? So we plug this delta here, and we find out this energy of actual loading, right? So we can take the integration of the small energy with respect to the force, right, to get a deflection. Okay, so the additional energy or equals to the F squared times dx over 2 AE. A is the cross section, E is the Young's modulus. Right, so we can take the integration to get the straight energy. Take the integration and take the integration and get this straight energy for actual loading. Okay, and for direct shear V, right, direct shear V, whose straight energy equals to the integration of the V square, V is the shear force divided by 2AG. G is the shear rigidity. Okay, for the torsion, the straight energy for torsion equals to the integration of the T torque square divided by 2JG. J is the polar moment, and G is the shear rigidity. Okay, and then for bending, so as already discussed previously, the U equals to the M squared divided by 2EA. Okay, so I'm gonna skip this mathematical work, or rather can study by yourself. It's not so difficult. Okay. So the final one is for the transverse shear. Okay, transverse shear. It's similar to the direct shear. However, we have to add up with the constant. the shape constant. Okay, so if this being or component with different cross-section shape. Okay, so C equals to 1.2 for rectangular, C equals to 1.11 with the circular cross-section, okay, and so on, okay, and so on. Okay, and then we can summarize strain energy corresponding to the different loading, right? So for the torsion and compression, which is the actual load, right? And this is strain energy. For direct shear, okay, direct shear, pure shear. Okay, so this is strain energy. Okay, for the bending, and this is strain energy. Okay, and for torsion, this is its strain energy. And for transverse shear, and this is strain energy. Okay, and where C is the modifier depends on the cross-section shape, right? So what I mentioned before. Okay, so this is what usually used for the transverse shear, the vector C. Okay, vector C. Okay, so today I'm gonna stop here and here, and next I'm gonna tell you how to use those this Cartesian theory to solve to figure out where's the maximum deflection or where is the deflection without any force applied. That's called a dummy load. We have to apply a dummy load at that location. Okay, so I'm just introduce the theory of the Cartesian method. Okay, so next chapter I'm gonna discuss more about how to use it and what's the application of the Cartesian theory is. Okay, so okay, so we'll stop here. So see you next time.